Hi everyone, I'm Ethan from Microchip Technology. Welcome to our Peripheral Deep Dive series. In this video, we're taking a deep dive into the Peripheral Touch Controller, or PTC, on our 32-bit microcontroller devices and how it enables capacitive touch in your designs. This is part one of a two-part series, and in this first video, we'll break down what the Peripheral Touch Controller is, where to use it, and how it works at a fundamental level. Then in part two, we'll move into a hands-on demo and walk through configuring the Peripheral Touch Controller on a 32-bit device using the MPLAB extensions and VS Code. So let's start with the fundamental question. What is the Peripheral Touch Controller? The Peripheral Touch Controller, or PTC, is a hardware peripheral integrated into our 32-bit microcontrollers that enables capacitive touch. The Peripheral Touch Controller allows the microcontroller to sense user interaction on a capacitive touch surface by detecting small changes in capacitance. These touch surfaces can be implemented as buttons, sliders, wheels, or other electrode shapes depending on your application. The Peripheral Touch Controller handles the touch sensing itself, while Microchip's touch library builds on that by converting those measurements into simple usable touch events like button presses that your application can respond to right away. With that foundation of the Peripheral Touch Controller in mind, the next question that we'll talk about is what applications do you see capacitive touch and the Peripheral Touch Controller used in? In home appliances, capacitive touch is commonly used on products like ovens or washing machines, where smooth touch keys and sliders replace mechanical buttons and create sealed surfaces that are easy to clean. In home touch panels, it appears in systems such as thermostats or keypads, offering compact, modern interfaces without added mechanical complexity. Capacitive touch is also used in industrial environments, including equipment interfaces, where reliable user interaction is required. Beyond the user interface, these applications that we just talked about must also be designed for efficiency and dependable touch performance. So let's talk about how the Peripheral Touch Controller helps with that. When paired with low-power features on our 32-bit microcontrollers such as event system and sleepwalking, the Peripheral Touch Controller can continue monitoring touch inputs while the main controller remains in a low-power state. This helps reduce overall system power consumption without sacrificing responsiveness. For more information on the event system and sleepwalking, we'll also have peripheral deep dive videos on those, so be sure to watch those ones as well. Many designs also need dependable touch performance in challenging conditions, such as moisture on the touch surface. To support this, many implementations of our Peripheral Touch Controller include driven shield techniques. This feature helps stabilize the touch signal and maintain consistent detection in rugged conditions, making the Peripheral Touch Controller a strong fit for demanding applications where dependable touch behavior is critical. To see whether the Peripheral Touch Controller in a specific microcontroller supports driven shield, please refer to the device's datasheet. Now that we talked about where capacitive touch and the Peripheral Touch Controller is used, let's take a step back and look at what's happening inside the hardware of the Peripheral Touch Controller. Everything starts with the touch surface itself. The surface is created using capacitive electrodes on a PCB or conductive layer shaped as buttons, sliders, wheels, or other layouts depending on your application. Once you have your touch surface, the Peripheral Touch Controller supports two sensing methods, self-capacitance and mutual capacitance. In self-capacitance mode, each touch electrode acts as its own sensor, and the Peripheral Touch Controller measures its capacitance relative to ground, making this approach well suited for simple buttons and basic slider designs. With mutual capacitance, two electrodes work together. One electrode drives a signal, while the other monitors how that signal is affected. The Peripheral Touch Controller uses this interaction to detect touch at their intersection, enabling layouts like keypads, wheels, and multi-segment sliders. Once the touch surface is defined, the Peripheral Touch Controller handles the measurement process internally. During an acquisition cycle, the input control block selects the electrode being measured and drives it through a controlled charge and discharge sequence. When a finger approaches the surface, the electrode's capacitance changes, and that change alters the response during this cycle. At the same time, the Peripheral Touch Controller can apply driven shield. When driven shield is enabled, a nearby electrode is driven alongside the touch sensor to reduce noise and improve measurement stability in more rugged environments. From there, the signal passes through the compensation circuit, which helps stabilize the measurements by accounting for offsets and slow changes. The charge integrator then measures the electrode's charge behavior, and the on-chip analog-to-digital converter digitizes that result so it can be evaluated by the microcontroller. If the change is large enough, the Peripheral Touch Controller recognizes it as a valid touch, and a corresponding event can occur in your application. So that's the core idea behind the Peripheral Touch Controller. It continuously monitors the touch surface, evaluates changes in capacitance, and delivers reliable touch information to the rest of the system. At this point in the video, we've talked about what the Peripheral Touch Controller is, where it's used, and how it works internally. With that foundation in place, that's going to go ahead and wrap up part one. In part two, we'll move from theory to implementation. We'll walk through configuring the peripheral touch controller using Microchip's touch library and MPLAB code configurator using the MPLAB extensions within VS Code on a 32-bit device. For more peripheral deep dive videos like this, be sure to check out our channel for additional content. Thanks for watching, and we'll see you in part 2.